So dx dt then is this rate of change of x with respect to t. That's what dx dt is, okay? Now, when we say that something is directly proportional, we can say that it is equal to some constant, k, times the function, x. So this kx is the directly proportional part. So directly proportional is this part. So if we take what we just learned about differential equation, okay? We have a few different letters here. Instead of x and y, we have x and t. But the idea still remains the same, that we want to separate and we want to integrate, okay? So how might I separate this equation so that I have my x and dx's on one side and my dt's on the other side?
Get dt on the right side through multiplication, and then x on the left through division.
All right, so we'll start off with that very similar idea where we multiply that dt to the other side. Good. And then we're going to take that x and we're going to divide it to that left-hand side. So we get dx over x equals k dt. From here, once it's separated, now we can integrate. So we're going to be integrating 1 over x dx, and we're going to be integrating k dt. So this left-hand side, that's just going to give us the natural log of x. Okay. The right-hand side, what is that going to give us?
Kt?
Yeah, kt. And then we have to consider our plus c, all right? Now, let's for a moment look back at the top, okay? There's one phrase that I didn't highlight and that we didn't talk about. And that is this: x is greater than 0, okay? So if we initially state that x is greater than 0, what that means is I don't really need these absolute value bars for my x, because I already know that I'm only going to have positive values of x. So we can actually streamline this just to say natural log of x equals kt plus c. And these assumptions really come from like the examples we're going to see. We're going to be looking at populations, we're going to be looking at temperature, and for the most part, we're going to have sort of a baseline where it's not going to go below a certain value, so we don't need to consider the negative cases, all right? Now this hopefully looks kind of familiar from what we saw in the very beginning of 19.1. where I said, hey, this is an implicit solution, but I'd like us to find the explicit solution, okay? Now, how did I find the explicit solution when we had this previously?
You did e to the ln x?
Yeah, exactly, okay? So that's the same technique we're gonna do here. So we have e to the natural log x equals e to the kt plus c. Okay. All right. On the left-hand side, we now have x. On the right-hand side, how did we split that before?
Times e to the c. Or e times e to the c. And then
Whoever's speaking, your volume is super low. I'm really having a hard time hearing you.
I think she left and she's coming back.
Oh, okay.
She
Did anyone else hear her? What did she say?
yeah, she said e to the c.
As just that part, e to the c?
Times e
No,
to the
e to the kt times e to the c.
Yeah, okay. All right, so e to the kt times e to the c, right? And that's just using our exponent rules to simplify. And then I was like, okay, well, mathematicians are pretty lazy. Anytime it's just a number, right? E to the c is a number. So we're just going to write this as c e to the kt. Right? So this process here, are there any questions about this process?
Yes, for the previous one, we kept the absolute value when we canceled the e and the ln. But for this one, we didn't.
Yes, that is correct.
Is there like a specific reason why? Okay.
Yeah. And when we work in real world scenarios, especially if we're thinking about population, like we don't really have negative population, right? The population
Yes.
has to be greater than 0. And so when we're applying it to like a real world context, we can make some of these assumptions, and therefore it makes our equation a little bit simpler. Okay?
Yes.
All right. So here's the deal. I do not want to do this every single time I have a problem like we're going to see next. Okay. I don't think you do either. So the shortcut here, this is what we are going to be using. Okay. So when we're looking at these application problems of population growth and decay, here is what we can say. If dx dt equals kx, right? So if we have our initial, if we have our initial equation, our initial differential equation as just something that is directly proportional, like a kx, all right, then we know that x equals ce to the kt, all right? So we're not going to do all of that work like separate, integrate, e both sides, and then bring that constant down. We're just going to say if we know that this is directly proportional, like the rate of change is directly proportional, then this is going to be the equation that we need to solve. Okay? So we're not actually going to see a lot of calculus in these problems. What we're going to see is how do we connect this dx dt equals kx to x equals ce to the kt, and then just use that equation along with anything we've learned about solving exponential and log equations to answer the question. Okay? So on that note, let's do that. All right, example number 1. The number of bacteria in a certain culture increases from 600 to 1800 in 2 hours. Assuming that the exponential law of growth holds, find a formula for the number of bacteria in the culture at any time t. Then, what is the number of bacteria at the end of 4 hours? Okay. So here's what we see. We see that it follows the exponential law of growth. That translates to saying you have dx dt equals kx. All right. Exponential growth really means that you have the rate of change being directly proportional to your x of t. And as soon as we know that dx dt equals kx, we can skip right to our general solution, which is x equals ce to the kt. Okay? Now, they've given us a bunch of information, but specifically, they've given us some initial condition. So what is x of 0?
600.
Yeah, it's going to be 600. And how do we know that?
Input, output.
Well, but how come it isn't like 1800? How come it isn't any other number?
Because that's their starting point.
That's the starting point, exactly. So x of 0 equals 600, and that is our initial condition. So what that means is at the end, we're not going to have a C in our answer. We're actually going to have a numerical answer for the number of bacteria at the end of 4 hours. And then when we write our equation, even when we write that formula, C will have a number, okay? So here's what we're going to do. We are going to go ahead and find our growth constant. So in general with these problems, a good first step is to find K. And we're going to find K using a lot of the information in the problem. So I know that at 1800 is the amount that we have at the end of 2 hours. Okay, so that's sort of my X of 2. My starting value is 600. That's our C. Okay, if you have a starting value, that is your C value. I keep the E, I keep the K, but T I change to 2. All right. So I use that whole first sentence. The number of bacteria in a certain culture increases from 600 to 1800 in 2 hours. I use all of that information. Now the only unknown I have is my growth constant. So I'm going to divide both sides by 600. I get 3 equals e to the 2k. And then I'm going to go ahead and solve for k. So I'm going to do that by natural logging both sides. So I get natural log of 3 equals 2k natural log of e. And natural log of e, that goes to 1. So really I have natural log 3 equals 2k. And that means my k equals natural log of 3 over 2. All right? So we found our k value. What that means is now I can write my equation, okay? So from here, we can write our equation. We can say that x equals 600 e to the t natural log 3 over 2. So this is our find the formula for the number of bacteria in the culture at any time t. So I have my x as x and I have my t as a t, so that when I plug in t, I can find the x that goes with it. So let's do that. To find the number of bacteria at the end of 4 hours, that would mean x equals 600 e to the 4 ln 3 over 2. Or x equals 600 e to the 2 ln 3. Okay, and when you type this into your calculator, you should get about this many bacteria at the end of 4 hours. Okay. Any questions about example number 1? Where things came from, where things went.
That last part for the answer, you just plugged in the calculator, right?
Yeah.
Okay, cool.
You could do this one by hand. I think this one's actually not so bad because it would equal 600 e to the natural log of 9, because 3 squared is 9. And that equals 600 times 9, which gives you 5,400. Okay, but most of the other ones, the numbers are not going to be quite so nice, so these will be calculator sort of problems. All right, let's take a look at another common scenario where we can say, hey, the rate of change is directly proportional to the function, okay? So radium decays exponentially and has a half-life of 1,600 years. That is, any given quantity, 1/2 of it will disintegrate in 1,600 years. Find a formula for the amount remaining from 50 milligrams of pure radium after T years. Then when will there be 20 milligrams left? Okay. So again, as soon as we see this exponential decay or exponential growth, like we did in number 1, that tells us that we have dx dt equals kt. And because we did all that work on the first page, we know that means x equals ce to the kt. Okay, so that's the calculus part, making the connection between these two pieces, all right? The rest of it is a lot of sort of pre-calc kind of work, all right? So in order to answer this question, we are going to find our k, just like we did in example number 1. So what are our initial conditions before we start finding k?
50 milligrams.
Can you please give it to me in the same format that we had our previous initial condition?
1,600 years.
500 equals C to the
C is not the initial condition.
Would it be x of 0 equals 50?
Yeah, we need a whole coordinate in order to say this is the initial condition, right? Because we have 2 variables. So if we only give one of them, that's just like saying, oh, the equation of this line is 2. Like, 2 what, right? So we need to be really thoughtful about how we set up our initial conditions, because a lot of times they don't tell you, here are your initial conditions. They kind of like imply it in the equation. And so we want to make sure we set ourselves up for success, that we know what number goes in for t and what number goes in for x, okay? So great job identifying the 50. Let's make sure we also have that 0 in there. And so when we set this up to find our k, we know that 50 is our C, that is the initial amount of radium present. I have E, I have K, and what do I put in for T?
1,600.
Yeah, now we're going to use that 1,600, right? Because that talks about the years, like how long something's going to happen. So what goes on the other side then?
25.
How did you get that?
Because it's the half-life formula.
Beautiful. Exactly, right? They didn't give it to us. Nobody told us, oh, hey, 25 milligrams. But it was implied because they say half of it will be gone in 1,600 years. Okay. So now we can solve this very similarly to how we did the other one. I'm going to divide that 50. That's going to give me 1/2 equals e to the 1,600k. I'm going to natural log both sides. And here's what you'll see in a lot of the answer keys or explanation. So I just want to clarify where this next part comes from. There's nothing wrong with saying natural log of 1/2. Okay, there's nothing mathematically wrong with that. Most of the time, though, folks don't write it like that. They write it like negative natural log of 2. Okay. So natural log of 1/2 is the same as negative natural log of 2. But let's figure out how they got that. So they applied the quotient property for logs, which means log of the numerator minus log of the denominator. Right? And then nice value to know, natural log of 1 is?
0.
Yeah, 0. So when we simplify this, we get 0 minus natural log 2 equals 1600k. And that's why a lot of folks tend to use negative natural log of 2 instead of natural log of 1/2. Okay. My last step here to isolate my k is just divide by that 1600. So here is my k value. This k value tells me the relationship of how quickly this material grows or decays. Right? So if we put this back into our equation, our general equation, so we can find out the amount left at any time, is just going to be x equals 50 e to the negative t natural log 2 over 1600. All right, so let's find out when there's going to be 20 milligrams left. Okay. So there will be 20 milligrams left. That means x is going to be 20. So I'll have 20 equals that equation that I just wrote. First step here.
Natural log both sides.
Divide by 50.
Wait,
Yeah,
no, yeah, 50. My bad.
yeah, let's divide by 50 first. So 20 divided by 50 is 2/5. And e to the negative t natural log 2 over 1600. All right, now I'm going to take your advice and let's natural log both sides. So we've got natural log of 2/5 equals negative t natural log 2 over 1600. Now to isolate my t, I'm going to multiply by 1600 and then I'm going to divide by natural log 2 or negative natural log 2. So that'll give me t equals 1600 natural log of 2/5. So that's getting rid of the 1600 and then dividing by negative natural log 2 to get that negative natural log 2 away from the t. When you type this all into the calculator, okay, so these numbers are not as nice as the numbers we saw in example 1. This should give us about this many years, okay? So in about 2100 years, then you'll have 20 milligrams of radium left from your initial sample of 50 milligrams, okay?
Quick question.
Yes, sir.
If we come up with an answer, and let's say that we had 2100 15 years, but it was like 0.2 something, do we always round up to the next year?
It depends. I think that with rounding, especially with something as long as this, I think a whole year is fine.
Okay.
If you were working in a different context where maybe the half-life was significantly shorter, then maybe it would be important to include decimal.
Okay. I was only asking for the contents of like when we're doing the quiz.
Yeah, it does become really based on sort of the scenario. So when we're looking at like radium or carbon-14, those half-lives are so long that it's like, just go to the whole year, it's fine.
Because I know that with time it's one thing, but like with people, they'll typically say round up. Because I mean, if you have a population of 5,000.25, like you can't really have 0.25 of a person, so they just typically will round up.
Round down.
Or yeah, either round down or round up, one of the two.
You don't get an extra person. So I think typically we round down with populations. All right, so last example here. All right, we're gonna take a look at Newton's law of cooling. All right, so Newton's law of cooling, if you learned it in pre-calc or any of the other classes, was probably like this just really long formula, and you're like, I don't know where this formula came from, and we kind of get that formula from our differential equation, okay, which is pretty cool. So the rate at which an object cools is, here's that phrase, directly proportional to the temperature, the difference in the temperature between the object and the surrounding medium. So as soon as I see directly proportional, I'm like, yep, dx dt equals some constant times something. But with Newton's law of cooling, things cool at a specific rate, but they cool also depending on the temperature of whatever they're in. Okay, so the medium is not like a small, medium, large, but the medium is like whatever the object is in. So you take a pie out of the oven, you leave it on your windowsill, that the air temperature is your temperature of the medium. Or you take a metal bar that has been heated up and you put it in water to cool it off, the water is the medium. So the temperature of the medium is the temperature of the water, okay? So it depends not just on your object, but also on what that object is in. So what we're gonna say, instead of just saying kx, we're gonna say kx minus 75, okay? Because in this case, our medium temperature is 75 degrees. The air is 75 degrees, okay? Now, what that means for us, okay, let's do this the long way the first time, all right, because it does change a little bit. We can't just say x equals CE to the KT. We actually have to include that 75 somehow. So if I were to separate, I would do dx over x minus 75 equals k dt. I would integrate, I would get natural log of x minus 75 equals kt plus c. I would raise both sides to the power of e, so x minus 75 equals e to the kt plus c. I would split my e to the kt plus c. And then I would write my e to the c as that c in the front, okay? So most of it looks very similar to a regular growth and decay population situation. The one difference is you have to add that 75 at the end. So x equals CE to the KT plus 75, okay? So with Newton's law of cooling, we do have a slightly different equation, all right? But if you ever wondered why you were like sort of, it was like kind of exponential, but then you added some things to it, this is why, all right? This is where that comes from. But when we approach these scenarios, we really do the same thing where we have to find the cooling constant, and then we need that to answer the question, okay? So we're gonna go ahead and find K in a very similar process to how we found K in the previous question. So X equals my initial, finding my C. What is my C value here? How do I find that? Any ideas?
Your C value is 125.
It's actually not 125. Okay. But tell me why you said 125.
Because it cooled from 125, but did you already minus the 75?
Okay. The initial temperature is 125, right? I think we all agree that that initial temperature is 125, but it's all relative to the temperature of the medium. So what that means is C is really 125 minus 75. So it's the difference between your initial temperature and the medium temperature. Okay. So it's all relative to whatever the surrounding air temperature, the surrounding water temperature is all relative to that, okay? That means our C is not 125, but our C is 50. So if we go ahead and use our initial conditions or think about some of the other values we have, we know that it goes all the way to 100 in half an hour. Okay. Now, some of you might be like, well, how come you can just put 100 in there and not 100 minus 75? The reason is this 75 on the other side, when we subtract it over, that's where you get the difference from, okay? So everything is relative to the medium, the ending temperature, as well as the starting temperature, okay? So when we subtract this 75 over, we'll get 25. And then let's go ahead and divide this 50 at the same time. So we'll have 1/2 equals e to the k over 2. Now I'm going to natural log both sides. I know that 1/2 is going to be negative natural log 2 equals k over 2. So then k equals -2 natural log 2. Yes, Mariah, what's up?
My question is about the time. I remember back in pre-algebra days when we were doing like PERT, there were time could be months or min. You remember how there was the different ones? Are we just using half because that, or 30 minutes? Like, will it matter?
Because for this formula, it's the time is hours, so you have to use it in hours.
Mm-hmm.
Thank you.
Yeah. Okay. So we've got our K. Now the question says find its temperature at the end of another half an hour. So what that means is I want to find X. So let's fill in all the numbers we have. We have 125 minus 75 e to the k times t plus 75. Okay. So in another half an hour, we've had a full hour. That means t is going to be 1, right? Because a half an hour plus a half an hour gives me 1 hour. So then I get 50 e to the -2 natural log 2 plus 75. And when we plug that into the calculator, I believe we get about 87.5 degrees. So going right up until the very end of the class today, but hopefully this last example was helpful in terms of like where Newton's law of cooling came from and why we sort of have these extra like, you know, plus or minus that surrounding temperature piece, because again, it's about the object, but it's also about what that object is in. Okay, both of those have an impact on how quickly an object cools. All right, so I'm gonna go ahead and stop sharing my screen here. So thank you for the reminder to be recording this. I'm sure we would have been really upset, especially folks who aren't able to make it today if we didn't videotape this.